The binding energies of deuterium and alpha particle are given. Well, deuterium is represented by 1H2, alpha particle represented by 2He4, and their binding energies are given per nucleon, 1.125. We can write 1.125 as 1.13 also, and then 7.2 MeV per nucleon respectively. In the process, 1H2 fuses with 1H2, there is formation of 2He4, the amount of energy transferred is, and which nucleus is more stable. Well, the binding energy of deuterium is given, so we multiply the number by 2, it becomes 2.25. Total binding energy, that will be 2.25 plus 2.25, it comes to be 4.5. Binding energy of helium nucleus, that is 4 multiplied by 7.2 because it is given in the question, it becomes 28.8. Helium in comparison to 1H2 and 1H2 has 28.8 minus 4.5 energy, that is 24.3 MeV more energy. So 24.3 MeV energy will be liberated. Also, higher the binding energy per nucleon for a nucleus, more will be the stability of that nucleus. So helium is more stable. The sixth example, deuterium is an isotope of hydrogen, that is 1H2, and its mass is 2.01470 AMU. Basically, deuterium is made up of one proton and one neutron. And when we take the exact masses of proton and neutron, for proton it is 1.007825, and for neutron it should be 1.008665. So here the deuterium is an isotope of hydrogen and it is a mass of 2.0147 AMU. Find the binding energy in million electron volt. Again, we are using a concept, that is 1 atomic mass unit is 931 million electron volts. The deuterium, the isotope of hydrogen, consists of one proton and neutron, as I have just now explained. Therefore, the mass of nuclear constituents, that is a net mass, will be 2.01657 AMU. Mass of the nucleus is known to us. We take the difference of two masses, and the difference will come to be 0.00187, and this 0.00187 is multiplied by 931, and that is called the binding energy, and that is 1.741 million electron volts. Well, in our next question, the binding energy per nucleon for 3 lithium-7 will be how much? If the mass of lithium-7 is 7.0163. So energy is delta E over A. This is the formula. That is delta M into 931 over A. Then we have taken 3 MP, means 3 times the mass of proton plus 4 times the mass of neutron minus the mass of lithium nucleus, which is given 7.0163, and we find that delta M we will calculate by subtracting the value. Mass defect is found to be 0.04216 AMU, and we find binding energy by dividing by 7, and it will come 5.6 MU. Now our question is that sun is radiating energy in all directions. The average energy received at Earth is 1.4 kilowatt per meter square. In a unit area, we get energy as 1.4 kilowatt. The average distance between Earth and Sun is also known. If this energy is released by the conservation of mass into energy, then the mass lost per day by Sun is approximately how much, where one day can be taken as 86,400 seconds. To solve this question, we will say Sun radiates energy in all directions. So we have to consider the intensity of radiation. Energy received per unit area per second, that is called intensity. It is 1.4 kilojoules. That is what given in the question in the second line. Therefore, the energy released in the area 4 pi r square per second will be how much? So 1.4 kilojoule is converted into joules. that becomes 1400, 1400 multiplied by 4 pi r square joule, the energy released per day. And then we multiply it by 86400 joules. Now, R is given to us, that is 1.5 10 to the power 11 meters. This is called astronomical unit. So, 1400 multiplied by 4 into 3.14 along with that distance to square, and the time gives the exact value. The equivalent mass is delta M is equal to delta E over C square. So, we compute the values, and the net mass used is 3.8 10 to the power 14 kilograms. Now we come to the ninth question, the energy released per fission. Now if one fission takes place from uranium, then 200 MeV energy is produced. A reactor is using uranium-235 as fuel, is producing 1000 kilowatt power. Then find the number of uranium-235 nuclei undergoing fission per second. So now the energy produced per second, that is known to us, 1000 10 to the power 3. So that will be 10 to the power 6 joule. We divide it by 1.6 10 to the power minus 19, and the result will come in electron volt. That comes to be 6.25 10 to the power 24 electron volts. We can remember that 1.6 minus 19 joule will be equal to 1 electron volt. The number of fissions should be, we have to calculate, so it is 6.25 10 to the power 24 eV, that is divided by 200 into 10 to the power 6, and the aggregate result will become 3.125 into 10 to the power 6. That is the number of fissions.